And welcome to Climate Chat. I am your host, Dan Miller, and I'm here with my co-host, Leon Simons. Welcome, Leon.
Hi, Dan. Good to see you.
So today we're talking about some recent research that talks about how both greenhouse gases and ocean heat content, two different papers on each of those, have been very stable for a really long time, going back 3 million years, and
Not the ocean heat content, just the CO2 and the methane.
okay, the ocean. Okay, well, we'll see more about that in just a moment, and there's big implications for our current situation in which greenhouse gases are not stable at all and going up at not 10 times, not 100 times faster, not 1,000 times faster, but way faster than what's happened on average over the past 3 million years. And so, Leon, I'm going to turn it over to you. By the way, so let me just first show the papers we're talking about. The first one is called Broadly Stable Atmospheric CO2 and CH4, which is methane, levels over the past 3 million years. And the other paper here is Global Ocean Heat Content over the past 3 million years. So those are the two papers. And Liam, why don't you tell us a little bit about these?
Yes. Yeah, I would have loved to have one of the authors on here, but we decided to cover this only yesterday. And yeah, I've been in touch with John Higgins, who's the author of both papers. And yeah, he said that a number of scientists are interested to explain this all in more detail. So I think,
and we can do that on another show. That'd be fine.
Because I'm not an expert on how to get this data. I think that's really let me show you this first.
And by the way, there are links to both papers in the description. Although I have to say it's a Nature they're both Nature articles and they're under subscription, so you can read the abstract and things like that. There may be ways to see it without payment online, but I'm not sure.
Yeah, I can share the paper if anyone is interested. Yeah, I think we should start by saying how an amazing achievement this is to get 3 million year old data from what the atmosphere looked like at the time, right? It's we used to like I have these like my geography books from university. We learned about these. I don't think you can see it, but we always learned about that the climate has been getting okay.
Yeah.
So you have all these different epochs, right? And you see this curve. I don't have the graph here, but I'm just to show you that we always learn about these different climate eras and how the climate has been changing over time, of course. And the past 3 million years, we have relatively okay data of oxygen isotopes. And again, I'm not going to cover that because many can do that much better than I can, but it's a way to see how high the temperature were globally, or how much the ocean temperatures were globally, and also how much ice there was, because there's these different oxygen atoms with different weights depending on the protons and the neutrons. And so there's mainly oxygen 18 and oxygen 16, and the difference between those can help us understand the climate of the past. But and you can get those from these small deposits of shells on the bottom of the ocean, for example. But what we didn't really have, we only had for the past 800,000 years, we've had access to these small air bubbles over this from this period, where from these ice cores from Antarctica, which gave us some insight in what the atmosphere looked like when those small air bubbles were trapped by snow and then more layers of snow, and then you have these small. Then the pressure turned that snow into ice, and that those air bubbles from hundreds of thousands of years ago were preserved on the very cold continent of Africa, of Antarctica, right? And what we didn't have, because of course the ice moves to the shelves and eventually melts, so we didn't really have this very old data from millions of years ago until they discovered this region on East Antarctica. Is it here? Or let me check. I'll go to it later. So yeah, here, right, this picture shows the drilling location where they were on East Antarctica to drill for this ice over 100 meters deep to get these very old ice bubbles because those were like preserved and frozen, literally frozen in time for millions of years. And it's really an amazing feat what they did here to even to go there, right? And then with this extreme climate that you have on Antarctica, which I would love to speak to those who went there and hear from them in more detail. I think we spoke with a glaciologist a few months ago who already gave some insight in that right then. So really great work, and I think this is the start of a lot of new research to come.
So 3 million years, just to give context, modern humans have been around for about 300,000 years. So this is like 10 times longer than modern humans have been around. So it's a long time.
And this was before Greenland was frozen, and before the world looked completely different. And as the title here shows, like that the CO2 was relatively low. I don't think that the warm spell. I don't know this from New Scientist, and their titles haven't gotten very good over the past years because I don't think it fully reflects the science or even the article itself. And it's better to look at the title of the Nature paper, where broadly stable atmospheric CO2 and methane levels over the past 3 million years. And that's one of the papers we'll cover today, and the other which was published on the same day and uses data from the same region, from the same ice core drilling. That's the title is Global Ocean Heat Content Over the Past 3 Million Years. And this study is led by Julia Marks Peterson, and this one is led by Sarah Shackleton. So yeah, these papers are really, I think, well written and relatively easy to understand if you get past their acronyms, and it's always with if you read scientific studies, you have to get a bit used to all these acronyms, and MYR means millions of years ago, and all. So these are all these 41 KYR means 41,000 years, and this relates to these
1,000 years. So the K, it looks when you read the graphs, it looks like they're saying thousands of years, but they're really saying millions of years because it's KYR, so kiloyears. Yeah.
Yeah, so this million, MA is million years. So
right.
Indeed, you have to know what you're looking at, and then it helps to look at these abbreviations. So it takes a while before you can read through these papers without having to think like what do these acronyms mean. But I think they both are really well written and easy to understand what they did here. And so this is the location. And both studies again look at the same region. So they took these in this region, and I would love to have one of the authors explain why this is such a a region where this is so stable, right? Where it has been, where you can find this millions of years ice, and it looks like this mountain range has likely something to do with it, right? Because here's the ocean, and so there's I think I remember that was part of the reason that the ice is stored there for such a long time.
Okay.
And what's important to know is that if you look at the CO2 and the methane measurements, of course there's some different, but they look at the longer time period and compare that also to more recent time periods from the past, so for 400, 800,000 years ago, to get a impression of not the variability. So because of there's within time, as you see here as well, there's some variability happening. But if you look at the longer time period, then you get you see the overall trend, and that's important to realize here, because that's really what this study does. They look at the long snapshot in time, because these air bubbles they found, they were compressed, and then so the ice that's hundreds of thousands of years old, rather than millions of years old, you get these bubbles, and you can get a more a clear indication of these variations. Again, this is these oxygen atoms, not the CO2 that's here and the methane is here. So for these past 800,000 years, we know quite well what the CO2 variability also was. So that's more like zoomed in, of course, from a geological perspective, right? Then you zoom in into a period of hundreds of thousands, 800,000 years, rather than looking at the millions of years trend. And then because of those were not decomposed as much as the older data, we can have this, and I hope we can get more information of the variability as well of the older ice. But this is now what we have to work with, and is already, as I mentioned, a great achievement that they got this number of what the atmosphere averaged over a longer period of time looked like.
Right.
And what they found was that the CO2 concentration was only, which is quite low, 250 parts per million.
So to put that in context, pre-industrial CO2 was around 280, and now we're at 420. Over the last 800,000 years, where you can see the lines going up and down there on the right side, the gray lines, that was CO2 going up and down to about 300 max, down to about 180 minimum. And the reason it's varying is because the Earth is going in and out of ice ages due to changes in the Earth's orbit and tilt. And those changes made the Earth get a little more sunlight, get a little hotter, and that led to more CO2 emitted, which led to getting warmer, which led to getting more CO2 emitted. So there was like an amplifying feedback. And at the
and
worst
vice
case,
versa when the glaciation happened.
and then the opposite happened. And when it's tilted away a certain configuration, it gets a little cooler, and therefore CO2 goes down, which makes it cooler, which makes it go down. And so what this all says is that, over the last 800,000 years, we knew we were a max of about 300 parts per million, a minimum of 180. But this now takes it back 3 million years and saying the average is naturally not saying what the variation is, but the average was even a little bit lower than pre-industrial, which is scary when you think about what we've just done in the last 200 years. I mean, it's shocking, actually.
Exactly, and that's, I think, what helps here is to realize. So I added this. So over these about 2 million years, the CO2 concentration, the average over a longer period, CO2 concentration decreased by only 20 parts per million. And that might not seem like a lot. And I think that's also what much of the media covering this show is. It's not a lot. And I I do agree it's not it's much less than most thought. But now, of course, you have these climate deniers saying, "Look, it's not CO2, doesn't do anything, right?" But it is quite a lot if you understand because how much it is really, because the decrease of 20 parts per million, that was relative to 250 parts per million, and compared to that, then because the effect of greenhouse gases and of CO2 as a greenhouse gas is logarithmic, which means that the smaller amount increasing or decreasing on the concentration from a small baseline has much more effect than, for example, if you would now add from the 430 parts per million of CO2 at 20 parts per million, then the effect is it's much less pronounced than if you decrease it from 430. So then the forcing is 0.45 watts per square meter. So it's almost half a watt, and that's I think we explained it a lot of times here on the show. A forcing is what forces the climate to change, and the unit here is a watt, which is a joule per second. This is the amount of energy per second averaged over the 510 trillion square meters of the Earth's surface. So how much heat is forced in, or forced in less, right, by these greenhouse gases if you have a decreasing forcing. So much less energy was retained globally. And of course, the Earth system responded to that. So that's on CO2. And methane stayed, according to this study, almost completely stable. Again, there's these variabilities
which and
didn't look at.
You can see the level there. It's I'm got to look it up here, but so today the level of methane is about 1.9 parts per billion. No, 1900 parts per billion. 1.9 parts per million, which doesn't sound like a lot, but it used to be. It looks like
it's off the chart here.
Around
maybe even off my screen.
It says about 500, right? So 500.
Yeah, but even if you look at here, it's like 550, 650. That would be like 750, 850.
Yeah, I'm just looking at the line down the middle. That line down the middle seems to be around
as a
500.
comparison.
So now we're essentially 4 times that level, is another way of looking at it. We're almost at, so this is 500 parts per billion. We're now close to 2,000 parts per billion. 1,900 parts per billion right now.
And that's also, if you compare it to this variability the variability of these 800,000 years, those only peak to about 700 parts per million, a bit off the chart here as well. But now we are at 1,000 parts per billion higher, which would break through my screen. And that's let's say here for a few seconds. So we changed it, and if you look at the 6,000 years from 6,000 years ago, about 6,000 years ago, until the pre-industrial revolution, the greenhouse gas forcing also increased. Well, based on the past glaciation periods, after a warm period that an ice age was starting, you would expect that the CO2 concentration and the methane concentration would be going down, but they increased instead. And one of the explanations for that is that humans started to burn forests and grasslands and
grow rice.
And grow rice for the methane. And so the early humans, of course not that early compared to the glacial periods and everything, but more the early agricultural civilizations of the past 6,000 years, with the Egyptians and all these civilizations that came and went. Those had been burning a lot of biomass as well, and increasing likely the atmospheric concentration of both CO2 and methane. And the effect of that is about similar to this increase of, or this decrease of 0.45 watts per square meter. Just
By the
to
way,
give an indication of,
0.45 is about it's like a Christmas light bulb over a square meter, maybe less than that. It doesn't sound like a lot, but there's a lot of square meters on Earth. And when you add it all up, I think 0.45 would be about 300,000 Hiroshima atomic bombs going off each and every day, that amount of energy. So you can imagine if there were 300,000 Hiroshima atomic bombs going off each and every day, it could heat up the oceans and things like that over time, especially over millions of years. I mean, yeah.
Exactly, over this very long period. And again, there was variability, of course, but
Right.
if this trend is correct, like over millions of years, of course, we do see this cooling trend, and which is more or less what this data set shows is oxygen 18 from foraminifera, from these small shells at the bottom of the ocean, shows that there was this global cooling, and these warm and cold periods varied with the periods of about 42,000 years first, and then later, which is really at the start of all these books, where you learn about geology and geography. Then you have this 100,000 year period where you have a cold period of about 80,000 years and a warm period of about 20,000 years. So there was a lot of change, and that also makes it a bit more and more complicated to assess how well the data from millions of years ago compared to the more recent data.
Okay. And
then again here, these oxygen isotopes, calcium, what is it, carbonate, and this is the delta, which means change of marine ocean temperature. So over this period, with this relatively small reduction in CO2 and a more or less stable methane concentration, they do show that the oceans cool down a lot over the same period. So you see this strong global cooling of the oceans. And of course, if you look at different regions of the ocean, some cooled gradually first and then cooled more. I think what is this? Or it's the deep ocean. DOT means of the North Atlantic. So yeah, again, takes a while before you can read what it is all said, but delta means change, and DOT here means the deep ocean temperature, and then this means North Atlantic. So the North Atlantic over this period cooled down gradually, more or less gradually, and then showed strong cooling. And I think that this is all hot from the presses, right? This is really new research. So there will be coming so much more research from based on this, because this is the first time we get an insight in this period where we didn't have much data on especially on the CO2 and the methane.
So do you have a feel for, that's how much, it's a little hard to see here, but whatever unit that is for the drop.
Which one?
I don't know, to pick any of these here. I'm just wondering what
this change in temperature. I think this
is temperature. It's gone down how much over
change in temperature here, and then here's the change in global sea surface temperature.
Okay.
This one, sorry, it's a bit. And so this is the North Atlantic. This is the deep ocean of the North Atlantic. This dark red is the deep ocean of the South Pacific. And this is the the mid-ocean temperature or marine ocean temperature. Right?
So that it dropped a certain amount over 3 million years. I'm just wondering how much it's increased in the last 50 years.
Yeah, I think it depends a bit on where you look, but it's
sure.
Yeah. Again, this will be there will be a lot of follow-up research on this, right? And I will be looking at this data myself as well in more detail in the coming weeks, and how it compares to the more recent data sets. And but I think what's important to realize then is here. Yeah, I think this may help a bit to understand these changes. It relates to your question, and I would have to. Well, this paper is called what is the name? The Global Ocean Heat Content over the past 3 million years. I haven't found the ocean heat content numbers yet. This is sea surface temperatures, so I'll reach out to the authors. But this is from the same author, Sarah Shackleton, who's the lead author of this new study. She also published a study where they looked at the ocean heat content and the global ice using also these different isotopes, and then they converted it all to global energy, to a global energy anomaly. And this is the unit here is thousands of zettajoules.
This is, I think, the biggest number I've seen on a graph like ever. It's one. How many zeros after that? It's a lot.
24, as it mentions here.
24 zeros.
So this is
big. I think is the way.
Sorry?
You could say. You could say it's a big number.
Yeah, and I could have made it 25, and then this would be 2.5 with 25 zero. But it's called a yottajoule.
Yottajoule.
Yottajoule. I think it's double T. And so that's a yottajoule is a thousand zettajoules, maybe.
As everybody knows. I mean, this is very common. People use these numbers
my
in their
kids
everyday
know.
life. Yeah.
My kids know if I ask them how many zeros does a yottajoule have, they'll say 24.
Okay.
And I have a cousin whose name is Jotte, and they said, then they tell him, Jotta, you have 24 zeros.
Okay.
So it helps them remember. But these are indeed like enormous amounts of energy. If you look at the last interglacial, which is called the Eemian. I live in Eemnes, so very close to my house. They discovered that there used to be ocean where I live, because then the sea levels were 5 to 10 meters higher globally. So we had Mediterranean. They found these shells that can now be found in the Mediterranean, and they are not native to our oceans anymore because they're too cold. So we had warm oceans covering the Netherlands at the time, and as you can see, there was more heat in the Earth system at the time than there is now. But we are rapidly surpassing, and most likely will surpass, this Eemian peak within I think decades even, because the Earth is energy imbalance. So the rate at which heat accumulates on Earth, on our planet, is really extreme, about 1.4 watts per square meter. And the greenhouse gas forcing now is 4.1 watts per square meter. So within about 200 years, we increased the concentration, the radiative forcing of greenhouse gases more or about as much, and it will be more if we keep going, than happened naturally, the decrease that happened naturally over a period of 2 million years. And now within a decade, around a decade, if you look at the greenhouse forcing increase now, within a decade, we increase the atmospheric greenhouse gas forcing. If you add up this methane and these other greenhouse gases, these novel gases which haven't been in the atmosphere of Earth at any time in history, we made those chemically. Those are also in the atmosphere, also increasing how much heat is retained globally. So if you add this up, we increase the greenhouse gas forcing within about a decade, as much as the long-term average decrease of over these 2 million years was. That's really mind-boggling, and we will continue to do that in the future if we don't change our ways. And of course, I think that's also, can go back to this, but it's important to realize that you have this, for example, this 350.org saying which CO2 concentration we need to go to stabilize the climate. I think that's led by Bill McKibben then.
Okay. What was that? Right. What did you say?
The 350.org.
Yeah, well, he founded it, yeah.
He founded it, yeah.
Yeah.
And I think James Hansen was also involved, but based on this
study...
The
name 350, for those who don't know, the name 350.org comes from the fact that Jim Hansen said the highest possible safe level of CO2 is 350 parts per million. Already it was 380 or something when he said it.
And it was 350 when I was born, so you cannot blame me for climate change because we already passed that point when I was born.
Okay. Anyway, so that's where the name 350.org comes from.
Yeah, and then if you look at this, so you have these different, I think we will not go into all these names, but the mid-Pliocene warm period, I think, is a bit before this study. But the sea level was at the time about 25, and so there was this change from 3.3 to 3 million years ago. And I think their CO2 estimates might be wrong. The estimate of CO2 concentration at the time, because we didn't have the data yet, but now we do. We do have an indication of what it was, and it looks like it's much lower. So at a lower greenhouse gas concentration, less CO2 and probably also less methane than most estimate at the time for that time period. The global sea levels were up to 25 meters higher than they are today.
Right.
And I think that's really crucial to understand. And even also during the last interglacial, like the last in the Eemian again, the sea levels were also, again, 5 to 10 meters higher than they are today, and already about the temperature we have now.
So no way putting it, the last time CO2 was the level it is today, 420 parts per million, sea levels were about 75 feet higher than they are now. And it takes a long time to melt ice, but that's actually and we're going higher than that. And that doesn't include the other greenhouse gases, which makes it even much higher. But we're on track over time for a very, very high sea level rise. It might take a little while to get there, but even 10 feet, which could happen in 100 years, is absolutely devastating for human society. Also, on this chart, something that comes up with deniers all the time Twitter is just a cesspool of climate denial now. And they always claim that, hey, there used to be higher CO2, so everything's fine. Doesn't matter if CO2 goes up, because a long time ago CO2 was higher and there were animals around then. But if you take a look here, it says that the temperature was 15 C higher than pre-industrial temperatures when it was like 2,000 parts per million, or between 1,000 and 2,000 parts per million. So
and the sun has been getting stronger as well, I think, and that's an important thing they don't include when they show these CO2 concentrations and temperature estimates from
that's right.
from the past something like 500 million years, right?
And as Kevin Anderson said on the show, like 4 degrees Celsius warming, and then he revised it to 3, is not compatible with an organized global community, or in other words, civilization. So 15 is not absolutely not compatible there, and not compatible with the human species probably as well.
And yeah, well, I think we're quite adaptive, but at least not with 8 billion people going around.
Right.
And yeah, and we are now at 560 parts per million.
When you include the other greenhouse gases.
CO2 equivalents.
Which is a doubling, which happens to be from 280 to 560. And ECS, or equilibrium climate sensitivity, is defined as the temperature you get, quote, in the short run, and the short run is thousands of years, for doubling of CO2. So that means if Jim Hansen's right and Leon's right, we're headed to without further increase in greenhouse gases, which we are continuing to do, but we're on the way to 4.5 degrees of warming in the quote near term, whatever that is. Now, of course, if we keep pumping up CO2 and other greenhouse gases, we can hit 4.5 without having to wait a very long time for it. So, yeah, like the end of the century, for example, as opposed to hundreds of years, maybe.
Yeah, okay. And even more than that, if we have these stronger feedbacks, and if we reduce the air pollution again from this from these forcings, if we reduce the air pollution, and that will materialize into a stronger positive net forcing. That's of course what we could experience, because that's this greenhouse gas forcing increase is partially hidden by the air pollution that lowers the net forcing. I've shown that a few times in the past months during Climate Chat.
Okay.
So I think that's a slide I have, and I would love to speak with the authors for more in-depth insight in how they got these numbers, what they show. But it's
So maybe you could just go over one more time, just kind of to summarize.
Yeah.
Just compare what the 3 million year numbers are versus the last 100-year numbers, or 200, however you want to count it. Like, what happened to CO2 over 3 million years compared to what we did to CO2 over the last 100-something years?
Yeah. So, are you asking me, or?
Yeah, I'm asking you to just summarize that again, because I think that's such a key point of these papers.
Yeah, over the gradual change over 2 million years. If you look at the past 200 years to what we did with all these greenhouse gas emissions, the effect is within 200 years is about 10 times the natural decrease that happened over 2 million years.
No, isn't it much more than that? Well,
10 times.
No, 10 times. No, yeah. You're right. Yeah. And I put another way, what took 3 million years to happen happens now in less than 10. We go up No, we go up about 30 parts per million in 10 years now.
Yeah, and again, so because it's logarithmic, that does change things a bit. But again, over 2 million, like who cares about whether it's 3 or 4, 2 or 3 million years or 10 or 15 years, right? We within decades, we are changing the atmosphere more than the natural change that occurred over 2 million years ago. Over 2 million years, from 3 to 1 million years ago.
Wow.
So, yeah, we're really a force of nature.
We're running an experiment. Yeah, I wonder what happens if you double greenhouse gases, in a snap of a finger kind of time frame to the Earth. It's pretty scary.
Yeah, that's what we're doing. And yeah, well, I wrote it here. Let me check how I phrased it.
Do you want to go on to questions or?
Oh yeah, sure.
So let me get back to here. Stacy, let me know when you're ready, and maybe I'll first go to. Well, Stacy is here. Okay. Let's first go here, and then. Welcome, Stacy.
Hi,
Where the
Dan.
cat?
Hi, Leon. No, I don't know. Rocky was moaning in here earlier, but they ran off. So I don't know.
Okay.
Maybe they'll be back.
Okay.
So just a few questions. Well, the one easy one is, did you do all these graphics, Leon, or are they from the paper?
One is mine, the ocean heat content data, but it's very much based on the 2023 study.
So the three selected global climate indicators covary across multiple paleoclimate.
That's an IPCC figure from. Where's I thought you had the question up. That's an IPCC figure, I think, from IPCC AR6 Workgroup 1 technical summary. I think.
Okay.
Might be the summary for policymakers or both, but that's. Don't know by heart. I should have put it there where the figure is from.
So the last one was IPCC.
Yeah, where you see these different climate comparisons.
Okay. All right. One from David. I noticed how quickly temps decreased in relation to CO2. Can the reemergence of stratocumulus clouds from a stratiform cloud-free paleoclimate explain this cooling beyond CO2 forcing alone?
Well, of course, one thing we know is that clouds are a feedback to CO2 warming, and we're seeing that right now. We had George Salutis on the program a couple of years ago now, a year and a half, looking at satellite data for the last 25 years and seeing that clouds are this was the big question mark in climate science. Do clouds increase with warming and therefore reflect more sun and therefore keep the Earth more stable? Or do clouds decrease with warming and therefore increase warming and have a feedback loop? And the answer is the latter. It's a feedback loop. And so definitely CO2 and clouds are linked together.
Yeah, I think this is indeed an really important question, because if the climate is more sensitive to a smaller change in atmospheric CO2 than most thought based on models, and I can show you that there's also comparison to some model studies here. But so if that's the case, you need stronger reinforcing climate feedbacks to explain the changes that happened from this smaller atmospheric CO2 concentration change. Because we know that the whole whole of Greenland freezed over, and the 3 kilometers of ice grew over Greenland, right? We know that happened. That we have the data for that. We understand that. We see that before Greenland froze over, there were trees growing there. I think over 3 million years ago. So And of course, the ice formation is part of the answer, because the ice reflects sunlight, so that's also part of the feedbacks. And the Arctic sea ice is also part of the answer. More Arctic sea ice reflecting more sunlight to space. And I think also the West Antarctic ice sheet. So not the part where they made they took these drillings, because there's been ice there for millions of years, right? But the other part of the Antarctic, this peninsula, the Antarctic Peninsula, that has been ice-free even during the Eemian. There's data based on these genetic fingerprints from octopuses, where you can see that these octopuses were able to transfer Antarctica, the West Antarctic ice sheet, which is only possible if there was no ice there. So we've seen all these changes, and based on these data sets from all these amazing scientists doing all this research, really at the most uninhabitable places on Earth, they're getting these answers for us, and we better learn from it, because they show that the climate is much more sensitive to our forcing agents and to natural forcing agents, but that also means to our forcing agents of increasing all these CO2 concentrations of these different gases than we thought. And of course, clouds are always a crucial part of it, and also one of the biggest uncertainties. So where do these clouds change, when, how long does it take, and how? Because if we would just be living on this black rock, then it would be very easy to calculate, right? If there were no oceans, if there were no clouds, if there were no aerosols, if there were no greenhouse gas, then it's very easy to do the math, and we that's really basic physics. But the Earth system is very complex, and we only have one, so we don't have much to go on.
I did smile when I saw the lead author's name was Shackleton.
What?
There is a question.
Wait.
Sorry.
I just let Eli in there.
Oh, yeah,
Let's see
please.
if he has a question or comment before we go to the other one.
Mhm.
So actually, we have a question from Blue Sky. Thomas Bocher
Okay.
asked, what was ECS 3 million years ago? I can partially answer it, but I want to ask Leon if these papers update us at all. A year ago, Jessica Tierney et al. In January 25 published a paper where they found, based on reconstructions and modeling, that ECS going back to that period was 4.8 C, and it was 4.1 degrees warmer at the time, from their data. Do these papers update that at all? Our best guess of both ECS in general, but I think the question really asked, what was it at the time, which is a slightly different question.
Yeah, I think that's one of the answers that will come, that will be informed by this research, right? Because if you don't know what the CO2 concentration was at the time, you don't really know how much, like what the system was responding to, how and how it changed, of course. So if the climate changed from 250 parts per million, again long-term average, compressed to a single bubble over, so that's data for, let's say, about 80,000 year average. Then if that trend, so if you look at the temperature trend globally caused by this forcing change, well, I haven't done the math here, but if we have multiple degrees of warming from only cooling, of only 0.45 watts per square meter of forcing, it it seems like the climate might be even more sensitive. But again, this includes, of course, long-term feedbacks. Right?
Also, I should point out that this is looking at ocean heat content, not surface temperature, and ECS is a measure of response of surface temperature. So
exactly, so
probably
you all need all
more
this
research is
information.
needed to figure that out.
These 2 papers, they just came out, and they will inform a lot of new research. I think really those making climate models, they will learn, they will use these numbers to run their models. These are mainly glaciologists and geologists trying to get the data and to do all this very complex chemical analysis and correcting for all these variabilities and trying to get the best answer they can get on what the concentration was. But then what that means for the climate at the time and for the current climate and how it will change in the future, that's not their job. That's a different specialty. So I think we will see a lot of people who do work with all these models, build on this. And of course, there are, as I mentioned, I think there are also some modelers involved here. So they did make a comparison. Maybe I can still show it.
Okay.
Let me check if I can include it. Should be in the supplement. And I was always, if you read the scientific papers, I always recommend to look at the supplements because there's a lot of important stuff there too, which you might miss if you don't.
I second that.
Let's answer before we go further. Let's answer a question from the chat of what is ECS, and essentially, I think I said it earlier. It's ECS stands for equilibrium climate sensitivity, and it is a measure of how much given amount of greenhouse gases change the temperature. And so the definition is if you double CO2, what temperature do you get? And the answer is the IPCC thinks it's around 3 degrees Celsius. And Jim Hansen and Leon and others think it's closer to 4.5. And again, that it could have been different back 3 million years ago. There are different factors in play. But that's what ECS is. It's a measure of how much warming a given amount of greenhouse gases change the temperature in the short to medium run. It doesn't include things like Antarctica melts and therefore it absorbs more sunlight, because that takes a really long time. So it's the stuff that happens up to about 1,000 years or so of feedbacks. Okay, so that's what ECS is, because we were talking about that quite a bit.
Yeah, and I just wanted to comment on the discussion about the methane graph. 2 points. First, it's not a high resolution thing, so there may have been, peaks that were too brief, because methane doesn't last very long in the atmosphere. It has a relatively fast half-life, certainly compared to CO2 or nitrous or nitrous oxide, N2O. But another way of describing that graph is the extremes were at around 700, right? And so we are pushing 3 times the extreme that we have in the geologic record. And people will typically talk about the greenhouse potential of different greenhouse gases. And like over a century, it's 20. A molecule of methane is 20 times more potent than a molecule of carbon dioxide. But in the first year, but that is relative to when it was emitted. And if you look at the concentration of the atmosphere, you have to look more like the 1-year global warming potential, which is between 100 and 120. So the 1 part per million difference is like 100 parts per million of CO2, which is why we really are closer to having doubled the pre-industrial CO2 concentration
have.
of 280
Equivalent we have.
ppm. Yeah, we're at 560 really
Yeah, even
when-
higher.
for greenhouse potential.
I think it's about 573 parts per million now in 2024, 2025. If you look CO2 equivalents, and then you don't
Which
take
is-
into account these aerosols, of course.
It's staggering.
Yeah,
Okay.
and let me get back to this, right? Because this is comparison to models, and this is again from the extended data and from the supplement. So they don't go into this in great detail, but so what they show here is that they show these different modeling studies. So that as comparison of these measurements from these ice cores, right, and then with model reconstructions from 3 million years to 500,000 years ago. And you see there's many modeling studies showing much higher CO2 concentrations to explain, in a way, of course, the changes that we saw.
Well, I think the overall summary of this paper is CO2 did not change very much over 3 million years. On average, there might have been fluctuations again, or ice ages and things like that. But it just puts in perspective the amount we're changing it now is so far out of whack compared to what's happened over millions of years on Earth is
Well, far and fast.
far and fast. Yeah.
And fast, and it's the
Again, in 10 years, we're changing CO2 more than it changed on average over 3 million years. In 10 years.
And the ecological impacts, particularly on things like extinctions, respond heavily to the rate.
That's right.
Is, what we're doing is just so unprecedented, other than things like meteor strikes.
Right. Well, even 252 million years ago, when there was a 6 degrees rise in temperature over a long time, because it was probably due to like certain volcanoes just constantly putting out CO2. So over thousands of years, not what we're doing now over decades and hundreds of years. But at 90% of all life, this 252 million years ago, 90% of all life on Earth perished. So it's not like, oh, things are fine when temperature goes up. Yeah, very, very serious. It's insane that, by the way, it's insane that no one's even talking about this stuff. I mean,
Yeah.
have you seen any discussion of climate change in the last on the news, on the mainstream news in the last few months? I haven't. So,
Well,
I think we should cut it. I think we should cut it to less than an hour here. We have 2 more minutes.
We have a couple more questions.
okay,
We didn't
what's
get through
that?
very many.
Okay, let's take 10 minutes for questions.
Yeah. How certain are the high Eocene CO2 values? Or is that a question for the authors?
The high IOC, wait. Which graph are they referring to?
What time is that?
1042 A. Scott.
Okay. Oh, this is the 1,000 to 2,000. Is that Eocene?
Or is it the last one? The
Well, I can't. I don't even remember what the
IPCC one?
The Eocene, yeah, I think that's the 50 million years ago, right?
Yeah, that's the one that's 15
What was
degrees
the
warmer.
question?
Right?
I think
How certain are those values of 1,000 to 2,000 parts per million? I think they have it a lot of different ways, right?
Yeah, I'm not an expert on early Eocene CO2 concentration reconstruction.
Okay.
But yeah, I think if you look up the IPCC AR6 work group 1, and then you look up where they got these numbers, yeah, I think you'll get more information.
Okay.
And at 1047, No War with Iran asked, what was the fastest sea level rise increase recorded in paleoclimate history?
I know Jim Hansen talks about at the end of the last ice age, it got up to meters per century, or I think like maybe a meter per decade or something. It was very, very high at the peak time when we're transitioning. By the way, during the last ice age, sea levels were 400 feet lower than they are now. Florida was 3 times wider than it is now. Of course, you could walk from Russia to Alaska and all that kind of stuff. So when that was ending and the ice caps were melting, sea level was going up very rapidly. And I believe the most rapid was on the order of a meter a decade. But or
And that
several
might be
years.
hard to imagine. But if you look at the Mercator Ocean estimate of how much the ocean heat content increased last year, which is still preliminary, but there was about 70 zettajoules. And if 70 zettajoules of heat is directed to rather than to heating the oceans than to melting of land ice, you'll have half a meter of sea level rise. And that's just from 1 year of ocean heat content increase.
But over what time, though, would that half meter?
What that doesn't matter. Like the heat equivalent of 70 zettajoules, if you use that heat to melt land ice, that ice would increase global sea levels by half a meter.
Yeah.
It's just referring to the amount of heat needed, not about time. So, of course, it takes time to melt ice, but if the ocean current, for example, change, or if you have a very strong rainfall, warm rainfall melting past the ice sheet, and part of the ice sheet, even if it doesn't melt, but it breaks off and enters the ocean, and then, of course, it also raises sea levels, right? It depends on the region, and it depends on the ice sheet stability and on transport of heat to the ice shelf. So there's a lot of things involved, but the heat is there. And we increase the heat in the system. And that, of course, now most of the heat goes to the increasing the ocean heat content. But as one of these graphs I showed you shows, is that, let me show you again. Or is it not? Where did I include it?
I'll also tell the story. I think I've told it here before, but I was helping Jim Hansen with his 2012 TED Talk, which you all should watch. And in it, he asked, while we're preparing, says, Dan, do you have a picture of Florida under 10, 15 feet of water? And I said, yeah, Jim, I do. But I think you should focus your talk on this century. And he goes, I am. I just went,
Bum, bum, bum.
what? And he said that now, if you talk to the IPCC or something, they say, oh, we might have 2 to 3 feet of sea level rise by the end of the century. And you got to remember, they're 95% sure of that, right? They're not telling you what they think the 50% value is, 50% probability value is, because scientists don't publish that stuff, right? They only want to stick with stuff they're sure of. But Hansen has said multiple times that if AMOC collapses, water stays close to warm water stays closer to Antarctica, you could get 10 feet of sea level rise in 100 years, or multi-meter is the way he put it. And and it might not happen, but that's the numbers we should be planning on, right? You plan for the worst, hope for the best, but right now we're not planning or doing anything. Actually, is what we're doing. Okay. Maybe a final question?
There are just
Or a
two that I
couple?
wanted to. One is, Leon, what do you consider ghost or phantom forcings?
I don't know. What do they think
I don't
of
know.
ghost or phantom forcings?
Like,
Is
what's
that
the
like the solar
definition?
force, the sunlight variability, if that is a forcing? Or
I don't know.
I don't know. What your I don't use that word often.
Okay.
Maybe they have a definition they want to share.
Okay. And then one.
I think this is
Yeah.
again the change in. So there were global cooling up until the oceans temperature, and then I think there's a glaciation, so the onset of the deglaciation. So again, look at the study in more detail if you want to understand where this energy goes. And again, this is really hot from the presses, and I expect in the coming years there will be a lot more research based on these findings, and hopefully also even more accurate and more detailed assessments of these ice cores.
Yeah, and there's someone in the comments talk about the Little Ice Age. The Little Ice Age was not the same as the Ice Age. It was more of a regional thing. There were a number of possibilities for what caused it, but it was not the same as a real ice age where ocean levels changed and things like that. It was just a regional cooling that was big. By the way, the point is it was a regional cooling. It had a really big impact on society back then, on farming and things like that. And yet what we're doing now makes the Little Ice Age look like just a one
Walk
day
in the park.
walk in the park or something. So and the same for the medieval warm period. Same thing. Regional warming, not a global phenomenon. Although this is things deniers talk about all the time. So they are real things, by the way. They're just not. They're not comparable to what we're talking about here.
They are straw men.
Straw men.
The last one is I'll give is from Nevitz. So what is the worst scenario if the oligarchs are allowed to run amok for decades and drill baby drill and burn baby burn? I mean, what and who will stop them? I'm not joking.
Well, the worst case scenario is we continue doing what we're doing. We don't take action to stop it. We talk a lot on this show what we could do to stop it. Actually, I'm giving a talk on that later in the week to a different group. But it's bad. It's like temperatures go up to 3 degrees in 2050s, 2060s. We hit 2 degrees late 2030s. And you get massive crop failures across multiple bread baskets. Right now we have crop failures across a bread basket. We have other bread baskets that take up the slack. But when you have it, you're going to have major cities running out of water, which is something that's happening right now, including Tehran just a little while ago. And, and just on and on and on. And then the catastrophes get so much that the governments can't keep up with them. And then you have collapse of organized civil society. A little Mad Max kind of thing, I guess.
I think that's almost the worst case scenario. The worst case scenario is that all of the things described in the question regarding the oligarchs and everything, the worst case scenario is that those don't matter because we've actually crossed over more tipping points than we realize. And the way to not have that be the worst case scenario is to get serious about sunlight reflection methods or solar radiation modification, because that has an immediate effect that can stop our advance over tipping points, even some of the tipping points that we otherwise would be committed to. So we don't have to be passive actors who are the victims of past inattention to how dangerous the situation is.
Yeah, we waited too long to those who say, hey, the only thing we should do is reduce our emissions. Well, first of all, we're not. But secondly, if we did, it would take decades to even notice that you did, because the temperature would continue to go up until you hit zero, and probably even after you hit zero. That's that's something you can debate, but it's certainly not something you can rely on. And it will take many decades to get to zero. And anyway, so we have to do everything. We have to get our emissions to zero. We have to remove the prior emissions of CO2 in the atmosphere, because they last there essentially forever. So we have to get rid of those. And we have to artificially cool the Earth while we do those first two things. And we are artificially cooling the Earth right now, just by accident. And we're doing it in a bad way that kills millions of people a year. So we should do it in a smart way that's much safer and takes a lot less pollution, if you call it sulfur pollution. and will be far more effective. And we've talked about that a bit on the show, so I'm not going to go into that.
You think?
Anyway, so really interesting study. As Leon is saying, this study is going to be sort of base research for many more from new studies that are going to use this information and try to calculate things like maybe ECS and things like that over time, and also map it to what that means for us now, changing greenhouse gases and ocean heat content so rapidly now compared to the past. So really eye-opening, and the fact that this, just to look back, that over millions of years, it changed an average of 20 parts per million over 3 million years, and we're doing that in like 7 years to change. It's like 3 parts per million per year now, which is insane, by the way. That number, it was 0 point something per year, before people were around. Very, very, very slowly change in parts per million. As this is saying, 20 parts per million. Now, it might change more rapidly due to temperature fluctuations during that time, but the average.
Yeah, our forcing change now is about 20 million% the natural decrease of 3 to 1 million years ago.
And 20 million% is a big number, I think. So.
Yeah, I think it's too big for people to comprehend.
Yeah,
not as big as a Jota Joule, but
okay. Well, very good. So, Leon, thank you for summarizing all this for us. Maybe we'll get the authors on, and they can go into more detail for it. And
that'd be great.
And thanks everyone for joining us. Please like and subscribe. It does help a lot. And share it with your friends. Hit the subscribe button. Leave a comment, by the way. And here's your question for your comment. Maybe leave it in the recorded one. Well, either one, but on the cover slide. And you have to do it based on what you've already seen. Now you can look at it in detail. We have a a graph behind the words 3 million year climate secrets, and it's a fake graph. My question is, did anyone notice it was a fake graph before I just told you?
I did.
So Leon did.
I didn't look closely enough.
Leon did, but that's my question for you, and you can leave that in the comments whether you noticed it ahead of time, not once you looked closely, now that you heard about it. Okay. Thanks everyone, and we'll see you next time. Bye-bye.
Bye.
Bye.